Hi, I'm Deb Floyd. This is my extra credit project for food chemistry. I would like to start with my textbook examples. Today I'm going to talk about acidulants and pH control, and we would define acidulants as food additives that impart a sour taste. They can be used for many different reasons, and they are excellent preservatives. We would define pH as the acidity, the alkalinity, or the neutrality of a substance, and we could say that pH is equal to pKa plus log minus salts over acids. They are generally recognized as safe by the FDA. Some common uses for acidulants are to provide sourness, to modify and enhance flavors, to lower the pH, to retard microbial growth, also to lower the pH in order to form gels and products containing pectin. We can increase buffer capacity, we can improve the texture, and we also prevent enzymatic browning. When we are looking at forms of acidulants that we would like to use as additives in products, we might consider their storage and handling issues. If they're liquid or dry, for instance, if you wanted a liquid product, acetic acid, lactic acid, phosphoric acid might be a good route to take. They are available in dry forms, but they are more expensive. We also want to look at combination of acids with similar characteristics and qualities, as well as their solubility. Some common acidulants that we use are acetic acid. We associate that with a pungent smell. It's commonly in pickling. We associate it with vinegar. And it's an excellent preservative in preventing microbial growth. Another one we might look at is citric acid. We commonly say that citric acid has a lemony flavor. It is a great antioxidant. It imparts a sharp flavor in like soft drinks. Used to stabilize emulsions, and we can now produce it through fermentation processes. The other that we might use is fumaric acid. It's not commonly used because it has very low solubility, and we manufacture it synthetically in the form of malic acid. The next one we're going to look at is lactic acid, very commonly found in fermented products. It's also produced commonly through anaerobic respiration. We also consider malic acid, which is found in apples and pears and tomatoes and bananas, and also in cherries. So we have our tomato. It's similar to citric acid in its uses, but it is more expensive. Another one we look at is phosphoric acid, very commonly used in the soft drink industry. We say that it has kind of a harsh, biting taste. It is the most commonly used inorganic acid, as most acidulants are organic. And the salts can be used as buffers. The last one we're going to look at is tartaric acid, found in cream of tartar. It's used as a bread improver. It's found in wines, and cream of tartar is used in conjunction and coordination with baking powder in leavened products. Some other sources for my information today could be found at chemistryindustry.biz, as well as understandingfoodadditives.org.
Hi, my name is Kelsey Darnall, and I'm going to be talking to you all about carotenoids. So the book pages that cover carotenoids and principles of food chemistry by demand, it's pages 244 to 252. Food Chemistry, Principles and Applications by Hui, Chapter 10, page 2, and Chapter 25, page 12. Food Chemistry by Belitz, Grosh, and Schauberl, page 18. Food Chemistry by Finema, pages 673 through 681, and Introductory Food Chemistry by Brady, pages 520 to 529. So just some background information about carotenoids. They are the most widespread pigment in nature. As you may know, they are red, orange, and yellow hues. In foods, they are dark leafy greens and then colored vegetables. Some examples are spinach and kale, and those actually are green in color because the chlorophylls mask the color of the carotenoids. And then also things like carrots, sweet potatoes, tomatoes, squash are all high in carotenoids. Carotenoids are only produced by plants and then a few microorganisms, but they can be found in some animal tissues if the food that they eat are high in carotenoids. One example would be salmon, which kind of appear orange in color, and that's due to the marine plants that the salmon eat are really high in carotenoids, so that's where they get their color from. Carotenoids are also found in chloroplasts, and they play an extremely important role in photosynthesis. They are secondary pigments in harvesting light energy behind chlorophylls. Carotenoids also have some antioxidant properties in vivo, and some serve as precursors to vitamin A, which is their most prominent role. The most prominent role of carotenoid pigments in our diets and in the diets of other animals. And for example, beta carotene possesses the most pro-vitamin A activity because of its 2 beta ion rings. And pro-vitamin A carotenoids in fruits and vegetables are estimated to have between 30 to 100% of the vitamin A requirement in human populations. So carotenoids are polyene hydrocarbons biosynthesized from 8 isoprene units and have a 40 carbon skeleton. And they're divided into 2 classes, which are keratines and xanthophylls, and keratines are hydrocarbons and xanthophylls are oxygenated. Some important structural characteristics to note are whether or not there's a presence or absence of oxygen, if there's an alpha or beta ion ring, the number of conjugated double bonds, and whether or not it's cis or trans formation. So now we're going to talk about some of the physical properties of carotenoids. They are hydrophobic, so they're soluble in fats and oils and acetone and ethanol. They're moderately heat stable, but they're subject to loss of color due to oxidation. And the color is actually a result of the conjugated double bond system. So the more conjugated double bonds present, the more red the hue. Next, the chemical properties. Carotenoids are very sensitive to oxygen and light, and as I just said, undergo oxidation very easily. So when oxygen and light are not present, carotenoids are generally stable at high temperatures. And oxidation is promoted with sulfites, metal ions, and lip oxygenase due to the presence of free radicals. But carotenoids also have antioxidant activity, so they're able to quench and inactivate singlet oxygen that are formed when exposed to light and air. And this quenching ability also depends on the number of conjugated double bonds. But when carotenoids are oxidized, they're actually completely destroyed. So in vivo, carotenoids serve as photoprotectors, protecting against singlet oxygen, and in vitro at low oxygen partial pressures, carotenoids inhibit lipid oxidation, and at high oxygen partial pressures, they act as pro-oxidants, such in beta carotene. So antioxidant functions in carotenoids are actually proposed to limit cancer, cataracts, arteriosclerosis, and the aging process. And there's a lot of research done about each one of these topics if that's something that you're more interested in. So now we're going to talk about isomerization. Generally, carotenoids are present in the all-trans configuration with the exception of algae, which are in the cis configuration. And large numbers of geometrical configurations can result from isomerization because of the large number of conjugated double bonds that are present. The more double bonds, the more possible configurations. For example, beta carotene potentially has 272 different cis configurations. And this is really important because beta carotene is responsible for the provitamin A activity. And when there's all trans configurations, there's 53% provitamin A activity, whereas cis there's only 13%. And they're not sure what causes this difference. So a quick note on the effects of processing. Generally, carotenoids are relatively stable during thermal treatments, but actually one interesting note is that blanching does increase the level of carotenoids because it inactivates lip oxygenase. But the most important thing to remember is that oxygen and light are the major factors in carotenoid breakdown. So if there's no oxygen or light present, they are really stable for thermal treatment.
Hi, my name is Alexis Meneese, and I'll be covering emulsions. The resources that I used were Principles of Food Chemistry by John DeMann on page 400, Food Chemistry by Belitz, Grosch, and Sherberly on page 63, and then Food Chemistry by Fenema on pages 134 through 138, pages 376 through 378. By definition, an emulsion is a dispersed system of one or more immiscible. With the exception of lecithin, all emulsifiers used in food are synthetic. And now I'll talk about the formation of an emulsion. To make an emulsion, you just need oil, water, and an emulsifier such as a surfactant. And a surfactant is just basically a material that strongly absorbs at the interface, and therefore it causes to substantially lower the surface tension at a low concentration. Proteins are the emulsifiers for oil and water food emulsions because they are edible, surface active, and provide superior resistance to coalescence. They can't be used for water in oil emulsions because they're insoluble in oil. You use an emulsifier for not only the formation of an emulsion, but as soon as you've created it, it will keep it stable. Next, I'll just talk about emulsifying properties such as like the physical chemistry of an emulsion formation and the factors affecting. We've talked about things like creaming, which is just where the particles like in the emulsion will separate, so they'll either float or sink. And then there is flocculation, which is basically just the opposite of an emulsion, where instead of binding together, they separate out from each other. There's also coalescence, which is just where it looks like the two solids are pulling each other apart, and then stability. Many of the everyday foods we eat, such as like milk, egg yolks, butter, mayonnaise, things like that, salad dressings, cakes, they are emulsion type products where proteins play a really big role as being an emulsifier in those products to bind them together. The homogenized milk is then more stable against creaming than the natural milk because of that casein micelle and whey protein film is stronger than the natural milk's lipoprotein membrane. To determine the emulsifying properties of a protein, you can look at a couple things such as like the size distribution of the oil droplets that are formed, the emulsifying activity, the capacity, and the stability. There are many different factors that influence emulsification. You have things such as intrinsic factors, which would be like your pH, your oil phase volume, the type of protein that's being used, the melting point of the oil that's being used. And then you have extrinsic factors such as the type of machinery that's being used and then the rate of energy that's being input. Just to reiterate, an emulsion is just basically comprised of two or more liquids that are just being bound together by an emulsifier such as a surfactant. Different things can affect them, such as pH, the type of machinery that you're being used, the energy input, the type of protein that's being used, the melting point, things like that. And basically, we see emotions every day. And that's all I have. Thanks for watching.